Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing about transition metal carbine complexes in the last few lectures, and we have looked into the various methods available with regard to synthesis of these transition metal carbine complexes as well as with regard to the properties of these transition metal carbine complexes. These transition metal carbine complexes are designated as something like this, where there is a multiple bonded carbine moiety with the transition metal. Now, these transition metal carbine complexes were discussed in the pretext of transition metal carbene complexes, which has this double bond character between the transition metal and transition carbonic moiety. Now, with regard to transition metal carbine complexes, what we had seen that they come in two classes. One is doublet carbine as well as the other one is a quadruplet carbine. Now, in the last lecture we had looked into the bonding or interaction of the frontier atomic orbital of this carbine moiety with the transition metal for this doublet carbine species. So, let us sort of take a look at how these frontier molecular orbitals are placed for these carbine complexes. What it has? It has a 1 sp A orbital which had 2 electron, 1 Pz orbital which has one electron and 1 Py orbital which is vacant. So, these are called doublet carbines, and these are mainly classified as Fischer carbine complexes. Now, we had discussed in details about the interaction with the these carbinic species with transition metal for this kind of Fischer carbine complexes, and what we found that these contains 3 kind of interaction. One ligand to metal sigma interaction, the next one is metal ligand pi interaction, and the last one is metal 2 ligand pi interaction. So, what we saw is that there are 2 dative kind of interaction. One is ligand sigma orbital donating to empty metal orbital, that is a dative interaction, and another kind of pi interaction which is also dative, where a filled metal orbital donating electron to the empty Py orbital of the carbonic moiety. And then we saw that one simple covalent half filled interaction between the metal d orbital as well as between the ligand Pz orbital which is partially occupied. Now, this is what we had discussed in our previous lecture about Fischer carbine complexes, which has doublet carbonic species bound to the transition metal. Now, in today's lecture we are going to be talking about the Schrock carbine species which are quadruplet carbenes. So, let us take a look at how these Schrock carbine species is, particularly with respect to its fragment molecular orbital. So, this also has sp a hybridized orbital, and sp orbital and pz orbital and py orbital similar to that of the Fisher carbine species, but what is different over here is the number of electrons in each of these orbital, as one in sp, one in pz and one in py. So, since this has a 3 unpaired spin, these are called quartet carbines or Schrock carbine. So, we are going to look in more details about how this Schrock carbine interacts with the molecular orbital of the transition metal having proper symmetry, and what kind of interaction these Schrock carbines lead to. So, the first one is so, this is a metal d sigma orbital, this is sp, pz, py, and the first one is just half filled interaction. Interaction between metal and the ligand, and this is denoted by metal ligand sigma interaction. The next interaction is between the metal d orbital with the pz orbital of the carbonic moiety, which has 1 electron, and pz also has 1 electron. So, this interaction is primarily between this metal d pi orbital and pz orbital, which is this, and this also is a half filled orbital, and the last one is between the p y and the metal d pi orbital and this is p y p z, and this also has one electron, and hence this is the interaction between P y and the metal d pi. So, this also is a half field interaction. And both of these interactions are metal ligand pi type interaction, and this one also is a metal ligand pi type interaction. So, what we see is the fact that these three half filled carbonic orbital, which is a p z, p y and one s p, each of them interact with the metal orbital having appropriate symmetry and also half occupied to give three multiple bonds between the carbonic and the metal fragment, and these three are pure covalent bond that involve sharing of electron from the metal fragment, and that they form metal ligand sigma bond, metal ligand pi bond and metal ligand pi bond in the process of such interaction. So, carbonic species, because of 3 unpaired electron, these are called quartet carbene as well. So, with this we have gotten a full insight as to how this carbine orbital, be it Fisher type or be it Strock type, interact with the metal orbital of appropriate symmetry and also electron occupancy to give these carbine complexes. And now we are going to look at some of the reactivity of transition metal carbine complexes as to how these interaction lead to the differential reactivity that these carbine complexes display. Now, one thing which is coming out from this discussion and also has been referred to as in our earlier lecture is that carbines are very strong pi acidic ligand, even stronger than that of the carbon monoxide, which usually is among the few benchmark strong pi acidic ligands that one actually refer to. And because of this, carbine exhibits extremely strong trans effects in substitution reaction. Trans effect means if a ligand which is attached trans to the carbine gets substituted during a substitution reaction, as carbine himself is strongly bound to the transition metal because of its 3 multiple bonds. So, reactivity wise, carbine exhibits strong trans effect in substitution reaction. Strong trans effect is a ligand found disposed trans to the carbine moiety would get displaced. For example, for this complex, when treated with a nucleophile like Y minus, gives So, what we see over here is the fact that the strands X gets replaced by this nucleophile Y, and this is because of the strong trans effect that this carbonic moiety is put. Here M equals chromium, molybdenum, tungsten, X equals bromide, chloride as well as iodide. The same can be seen that if this reaction is treated by C5H5 or cyclopentadienyl anion, then the product formed is eta 5 C5H5 CO2 M C R plus X minus plus 2 CO. And what it says that even CO can be substituted in these carbyne complexes. Usually CO is supposedly very strongly bound to the transition metal because of the forward as well as the backward sigma donation, but here is the instances where the carbonic moiety is bound even more strongly to the than the CO to the metal, and as a result in these carbyne complexes even the CO gets substituted as shown in the reaction. Now, carbyne complexes also undergoes nucleophilic attack, and this is similar to what we had encountered for carbenic complexes, and here is an example of the same. So, it undergoes nucleophilic attack at metal carbyne atom, and this is represented by this equation. Plus PME3, the PME3 attacks the carbonic carbon to give XCO4 chromium minus CpMe3 plus R, and this reaction is thus addition of phosphine yields phosphinocarbene. Phosphinocarbene. Now, one thing what needs to be mentioned over here is that because of this nucleophilic attack, the carbyne moiety is getting changed to a carbene moiety. So, the complex which is a transition metal carbyne complex over here becomes a transition metal carbene complex on going from here through nucleophilic attack. And what is to be remembered over here, that the reverse process of going from carbene to carbine was effectively used in synthesizing these transition metal carbine complexes. So, when we discussed the strategy for the synthesis of transition metal carbine complexes, what we had seen that the most of the transition metal carbine complexes were formed from the corresponding transition metal carbene complexes. Now, here we see that the cycle sort of repeating itself in terms of going back in the reverse direction, where these transition metal carbine complexes once formed when treated with nucleophile or undergoes a nucleophilic attack to give back the transition metal carbene complexes. So, what we see is a good amount of interchangeability between transition metal carbene and transition metal carbine complexes, and they have been favorably exploited not only for their synthesis, but also for their the reactivity studies, as is shown in the slide below. Electrophilic reactivity of carbene is higher and can be seen in the example discussed below. For example, for this Cp CO2 MnC methyl complex, when treated with methyl lithium, it gives lithium and reduces carbine to a carbene complex. So, what we see is that carbine complexes upon reacting with the methyl lithium gives rise to these carbene complexes. So, here also we see such carbinic moiety going back to carbonic moiety after the reactivity in the reactivity studies. Similarly, another example is known of reductive dimerization. And this can be seen for this chromium complex. Which in presence of NaPme2 eliminates sodium plus eliminates Me2P Me2 to give bis carbene complex. NET2. So, here what we see is that under these conditions the carbine moiety sort of becomes carbenic moiety, and then there is this dimerization happening to give this bis carbene complex, and hence this overall reaction is thus named as reductive dimerization reaction. Here is another interesting example of induced CC coupling observed for carbine complexes. coupling to give ketenyl compounds, and this is explained through this example. So, molybdenum carbide moiety when treated with PME3 have one of these CO migrate onto this carbide moiety to give this this CO inserted into the carbine fragment to give a ketyl moiety. So, what we see that there is this induced base induced CC coupling resulting to give ketyl compounds, which is this kind of species. Now, with that, let me conclude what we have discussed in today's lecture, particularly on carbine. We have looked into the metal ligand interaction using frontier molecular orbital diagram at the Strock kind of carbene, which has a quartet spin state. We have also seen how these carbonic moiety interacts with that of the transition metal, resulting in formation of 3 bonds, one metal ligand sigma bond, another metal ligand pi bond, and another metal ligand pi bond. With that, we also discussed about the reactivity of transition metal carbine complexes, and what we had seen that the reactivity sort of mirrors the synthesis of carbine complexes, but in the opposite direction, which is seen from the fact that much of the reactivity of transition metal carbine complexes lead to the formation of transition metal carbene complexes, and these transition metal carbene complexes were employed to synthesize transition metal carbine complexes. So, what we see is that much of the reactivity of transition metal carbine complexes lead to these transition metal carbene complexes. We have seen this with respect to the nucleophilic addition of the anions to the transition metal carbine complexes. We have also seen trans effect of the ligand situated trans to this carbine moiety getting substituted in the substitution reaction. Also, we have seen the electrophilic reactivity towards of carbine moiety towards reagents like methyl lithium, and finally, we have also seen dimerization of this transition metal carbine complexes, leading to the formation of these transition metal carbene complexes in this lecture. So, with that I would like to conclude today's lecture, and I will discuss some more of carbine chemistry in the subsequent lecture. Until then, that time, goodbye, and I hope to join with you in the next lecture. Thank you.